All right, so for number 5, I have, in my numbers, I have stated that 78% of adults surveyed want to live to be 100. If we randomly choose 5, what is the probability distribution that we'll have for each possible value of x? And so the problem says, hey, here's my x, there's 0, 1, 2, 3, 4, and 5. So if I randomly choose 5, 0 of them could want to live to be 100. 1 of them could want to live to be 100. 2, 3, 4, or 5. So we're looking at a binomial distribution. We have the same chance of success over a fixed number of trials, and it doesn't matter which one is first or not. So our formulae for the binomial distribution is this. And what we want to do is we want to use this with our p being 0.78, our q being 0.78, our q being 0.22, and our n being 5. Now again, my numbers might be different than yours because this does choose them randomly, and there is a little bit of a randomization that goes on with this. All right, so again on our calculators, so the p of 0 is going to be 5. Choose 0 times 0.78 to the 0th times 0.22 to the 5th. Now, if you look at problem 4, I showed you how to do this both on the TI-30 XSS and also on the TI-84 Plus. So I'm going to just type in the numbers. So 5, my probability key, choose NCR, 0 times 0.78 to the 0 times 0.22 to the 5th, and I get a probability of 0.000, and what they want 5 decimal places, so there's my 4th decimal place, and I get this. So that would go in here, 0.00052. All right, and I'll continue, and again, I will use up arrow to replace on my calculator the zeros with ones, and this particular 5 with a 4. And so let's see if I can get all those in. And I get for this value 0.00914. 0.00914. Notice these lower numbers have very low probabilities, which would be expected from something that has a 78% chance of success. All right, and so I'll continue with 2. So I hit the up arrow on the calculator, and I go back in and I change my values to match. And that's the same methodology that we had from problem number 4. 2, and 3. And now we have 0.064, 1, 2, 3, 7, 8. 0, 6, 4, 7, 8. Let me make my 9 look more like a 9 there. And we continue building our probability distribution. And so I'll put in 3s, again using the up arrow on my calculator to save me from having to do loads of work. 0.22968. 0.22968. And you can see the repeat. The thing on this problem is A, get comfortable with your calculator form for this, and B, make sure that we can recognize that it's a binomial distribution. Our chance of success is the same. We have a limited number of trials, and we have our probability distribution that falls out from that. And doing my last one here, or second to last one. And so 4 becomes 0.40717, and 5 becomes 0.22, or whoops, 288. I'm repeating 8s, not 2s. 0.28872. This then we can turn into a graph. And I'll do my graph here. So 0, 1, 2, 3, 4, 5. We'll have a very small distribution here. We'll have almost twice that here. This comes up much higher here. And then 3 is 4 times the height of 2, so it's up here. 4 is double the height of 3. Whee! And this is slightly bigger than 2. And so our probability distribution is going to look like this, coming across. Again, I'm not going to go through every step in the detail I did for question 4. Look at question 4 for your particular calculator and use that as your reference. But the idea is this is a binomial distribution, and it generates a probability distribution coming through. Now it does ask at the end of this question, what values would you consider to be unusual? And the rule we have for unusual is going to be anything that is less than 0.5. And so these first two values would be unusual. If you did the survey and no one said they wanted to live to be 100, that would be an unusual result. Grabbing 5 people randomly because of how the binomial distribution works out. Or if only one person said they wanted to live to be 100, then that would also be an unusual result because of these percentages being less, or these probabilities being less than 0.05. And so unusual things are less than 5%.